In this video, we're going to be looking at catalysts, which are a family of chemicals that are used to accelerate the rate of chemical reactions. Catalysts are different than simply adding in more reactants because catalysts are not consumed by the chemical reaction. This is very useful for chemical engineers because if catalysts are not consumed by a chemical reaction, that means that they are reusable. Biologists will recognize this definition of a chemical that is used to accelerate the rate of a biological reaction without being consumed by the reaction. For the biology students, if you think that this definition sounds a lot like an enzyme, that's because your enzymes are your body's biological catalysts. Now, catalysts function very differently than other factors that affect the rate of reaction. For example, temperature just simply adds kinetic energy to the reactants so that they move faster and are more likely to hit each other, while increasing concentration and surface area increases the number of reactant particles that can undergo a collision. However, catalysts do neither of these. Instead, a catalyst changes the amount of energy that is required to form the activated complex, E-min or EA respectively. And if a smaller amount of energy is required in order to form the activated complex, it becomes much easier for the compounds to react. Usually the way they do this is by bringing together multiple reactant compounds and allowing them to collide much more easily. This is specifically the way that most enzymes work. If we look at the mechanism of a specific catalyst in detail, we can take a look at this decomposition reaction of hydrogen peroxide, which is a spontaneous reaction. Hydrogen peroxide is normally a very unstable molecule, but the decomposition occurs very slowly unless we add a catalyst. When we add a catalyst, we can see that this reaction occurs in two steps, and if we simplify it in the way that we looked at when we looked at how to do Hess's law problems, we can see that there are certain compounds that we can cancel as long as they appear in both the products and the reactants. For example, this oxygen iodide polyatomic ion is a product of the first step, but then is consumed as a reactant in the second step. So we can cancel it and show that this is a clear example of what we call a reaction intermediate, which is a chemical that exists as a product of one step but is consumed before the reaction is over. If we look at iodide, however, we see that it's a little bit different because it appears as a reactant before it appears as a product, meaning that when it appears as a product in the final step, that means that it is left over. And why does it begin as a reactant? Well, if it begins as a reactant, it clearly is not an intermediate because it isn't a product that is consumed at a later step. And the reason why it appears as a reactant in the first step is because we put it there as a catalyst. So we can see that iodine appears in both steps, allowing it to be canceled, but because it appears as a reactant before a product, because we put it there, we can clearly identify that iodide is the catalyst in this case. And if we rewrite our equation where all of the intermediates and catalysts have been removed, we have two hydrogen peroxide molecules that we start with, exactly as in our overall, and we have two water molecules that it breaks down into with one oxygen gas molecule that is left over. So we see that simply by following the cancellation of anything that can be canceled out, we can end up with our overall reaction. Now, if you want to indicate that this reaction is catalyzed, we can write the catalyst above the reaction arrow like this to show that it is involved even though it isn't consumed by the overall reaction. Now, there is another family of chemicals that influence the rate of reaction, which are what we call inhibitors. Now, an inhibitor is basically the opposite of a catalyst in that an inhibitor is a chemical outside of the chemical reaction that actually decreases, or in many cases, prevents the reaction from happening at all, although the mechanism is usually significantly more complicated than with catalysts because multiple inhibitors have different mechanisms of action. Biological inhibitors very often will target the catalyst instead and prevent the catalyst from working. Enzyme inhibitors actually usually look very similar to what the reactant particle that the enzyme catalyzes, and if the inhibitor blocks the enzyme or blocks a catalyst from being able to work, it effectively stops the reaction from being able to happen unless we increase temperature. Many other inhibitors cause a side reaction to occur, producing an unintended product and therefore preventing the desirable products from happening. Naturally, many inhibitors that target enzymes within the body and prevent some of your most common biological reactions from happening, naturally these would be very dangerous, and so many inhibitors that target your body's catalysts are actually very, very deadly poisons. This concludes our series on factors that affect the rates of chemical reactions. In the next series of videos, we're going to look at how to use concentration in order to specifically calculate the effect of concentration on rates of reaction, and specifically how we can represent the actions of a catalyst on a potential energy curve.